Hello, welcome everyone. Today's lecture we are going to look at an example problem that concerns plane stress. So essentially you will be given some information about the stress and strain at a particular point, and given the fact that it is a plane stress problem, you should be able to calculate what the other stress and strain components are. Okay, so that essentially is the objective. So if you are given the stress and some of the stress and strain components at a point, and it is specified that it is under the plane stress condition, you must be able to use that particular information to evaluate the other stress and strain components at that particular point and then form the full stress and strain matrix at that point. Okay, that is what we'll try to learn here. Okay, so here is the problem. So essentially in this problem you are given that the point is under plane stress condition. So that is something that you must keep in mind because that is an information that we have to use to solve the problem. Okay, so it is under plane stress, that particular point. Okay, and it is also given that the epsilon x at that point is 4 into 10 to the minus 4, 4.5 into 10 to the minus 4, epsilon y is 10 to the minus 4, and gamma xy is 4 into 10 to the minus 4. Okay, so again I want you to note that this is strain, so it has no units. Okay, so strain is a unitless quantity. Okay, and apart from that, you are also given two other pieces of information. You are given that the shear modulus of that material is 100 GPa and the Poisson's ratio nu is 0.3. Okay, and this is information that we need because to relate the stresses to the strains, you need to know what the material properties are. You need to know the Young's modulus, the shear modulus, and the Poisson's ratio. Okay, and what it has to do is to determine the complete stress and strain matrices at that point where this information is given. Okay, so in problems like this, okay, the first thing that you want to figure out is which plane is the plane of plane stress. Okay, so is it the xy plane, is it the xz plane, or is it the yz plane? Okay, that is the first thing that you have to figure out because that will determine how you approach the problem. Okay, and usually when you have that question, the first thing you look for is that is any shear stresses or shear strains given. Okay, in this case a shear strain is given. Okay, and that shear strain is gamma xy. Okay, so gamma xy is 4 into 10 to the minus 4. So if you have a shear strain in a particular plane, then the plane stress is in that particular plane. So because gamma xy is not 0 here, the plane stress is for the xy plane, not the xz plane or the yz plane. And the reason is that if gamma xy is not 0, then tau xy is not 0. Okay, so the shear stress in the xy plane is not equal to 0, which means that there is a stress in the xy plane. Okay, and that means that it has to be plane stress in the xy plane. Okay, so that the fact that gamma xy is not 0 and it is given that it is plane stress essentially means that every stress component that has a z subscript is 0. Okay, so we have done two things. We have determined that it is plane stress in the xy plane, and as a consequence of that, these three statements are true. Sigma z is 0, tau xz is 0, and tau yz is 0. In addition, because tau xz and tau yz are 0, epsilon xz and epsilon yz are equal to 0. Because if you remember the Hooke's law, the shear strains only depend on the shear stresses. So if the shear stress is 0, the shear strain should also be 0. So if tau xz is 0, epsilon xz should also be equal to 0. So now if you think about what you have done, we have given only three pieces of information. Epsilon x is 4.5 into 10 to the minus 4, epsilon y is 10 to the minus 4, and gamma xy is 4 into 10 to the minus 4. Okay? Now, using that information and the fact that it is a plane stress problem, we have actually come up with another 5 quantities: sigma z, tau xz, tau yz, epsilon xz, and epsilon yz, all of which are equal to 0. So if you think about this problem, you have 6 independent stress components and 6 independent strain components. Okay, we were given 3 strain components. Okay, now we have determined another 5 stress and strain components. So which means that you have only 4 unknowns. Okay, so here I have put epsilon xy as an unknown. Okay, but it's actually a trivial unknown because epsilon xy is nothing but gamma xy over 2. So in some sense, you can say that you already know epsilon xy. It's just a factor of 2 for, multiplied with the gamma xy. Okay, so we have 12 unknowns usually, right? 6 strain components and 6 stress components. We are given 3. We have already found 5 more here using the fact that it's a plane stress problem. So we have 1, 2, 3, 4 unknowns still. Okay, so 12 minus 5 minus 3 is 4. So we have to figure out 4 of these unknowns. Okay, so that is the first thing you need to do. Figure out what are the things you can deduce based on the plane stress condition. Figure out what has already been given to you. Okay, and then identify what are the strain components and stress components you still need to actually calculate. Okay, so we have 4 to calculate. Okay, so that at least defines our problem pretty precisely. Okay, now before we go to actually finding out these unknown stresses and strains, we have to do one thing, which is actually find out the Young's modulus, because we are given the shear modulus and the Poisson's ratio. Shear modulus is 100 GPa, Poisson's ratio is 0.3. We still have to find out what the Young's modulus is, because that is something that you need for calculating the normal stresses. So in that case, you just use the formula that E is 2G into 1 plus nu. And if you use that formula, you essentially come up with a value of 260 GPa for the Young's modulus. So essentially we have the 3 material properties that we need, E, G and nu. And we have 8 out of the stress and strain components that we need. Okay, so once you do that, right, the first thing, of course, I identified epsilon xy is an unknown, but it's actually a trivial unknown. So that is nothing but gamma xy over 2. So essentially you identify that. Okay, but you still have 4 more to go. Okay, and the next easiest thing to figure out will essentially be your tau xy. And the reason is the shear stress only depends on the shear strain. And we are already given gamma xy, right? So essentially, the only thing you need to do is multiply that gamma xy by the shear modulus G, and you get the shear stress tau xy. Okay, so it's just a trivial multiplication. And if you do that, you get the shear stress to be equal to 40 MPa. Okay, so if you think of, we had 5 to start with, we've already found out 2 of them. Okay, so the unknowns still are sigma x, sigma y, and epsilon z. Okay, so for that, you again use Hooke's law, and we know that when you have a plane stress condition, the Hooke's law becomes a little bit simpler. So for example, epsilon x actually becomes an expression like this because sigma z is 0. So epsilon x is 1 over E times sigma x minus nu sigma y. Okay? Again, in this case, you still don't know sigma x, you still don't know sigma y, but we know what epsilon x is. That is one of the things that was given, right? Epsilon x was given to us. Okay, so that is, so you use that. So epsilon x is 1 over E times sigma x minus nu sigma y. Then you put in the values for epsilon x. Okay, you put in the value for E, which we just calculated. So one thing I want you to note here is that I have used 260 into 10 to the 3 here. That is because E is 268 GPa. Okay, and I want to calculate my stresses in MPa. Okay, so if I have to have my stresses in MPa, then I also need to change my Young's modulus from GPa to MPa. So 260 GPa is nothing but 260 times 10 to the 3 MPa. Okay, so that is why I have the 10 to the 3 factor there. Okay, so I use that particular value of E, and similarly, I can also write the expression for epsilon y. Epsilon y is going to be 1 over E times sigma y minus nu times sigma x. Okay, and epsilon y is given, which is equal to 10 to the minus 4. You know E, and again the 2 unknowns are sigma y and sigma x, right? So if you look at these 2 equations, 1 and 2, you essentially have 2 equations in 2 unknowns. The 2 unknowns are sigma x and sigma y. And of course, you know how to solve for 2 equations from 2 unknowns. And if you do that, you essentially get sigma y as 67.14 MPa and sigma x as 137.14 MPa. Okay? So we already know epsilon xy. we already found out tau xy. Now we have found sigma x and sigma y. So the only unknown that is still left is epsilon z. Okay, and again, I want to remind you that this is a plane stress problem in the xy plane, but the strain in the z direction, or the normal strain in the z direction, is not zero. So epsilon y, typically epsilon z, is typically not zero. Okay, and you can calculate what epsilon z is using this simple formula. Okay, again, this is just the Hooke's law with the condition that sigma z is zero. There's nothing unusual here. Okay, so it's going to be minus nu over e times sigma x plus sigma y. And if you put in the values, you essentially find out that epsilon z is minus 2.357 into 10 to the minus 4. Okay, so again, this is something that is easy to understand. So if you look at this particular problem, right, you have stresses in the x and y direction. We just found out that sigma x is 137.14, sigma y is 67.14. Okay, again, they have the same values in the opposite phase. Okay, you have this, and you have shear stress, which is, if I'm not mistaken, is 40 MPa. So essentially you have shears that go like this, like that, and shear again is positive, so I'm denoting in the positive sense. This is 40 MPa. Okay, so now if you think of this as a plate, you essentially are stretching it in the x direction, you're stretching it in the y direction, and you're also applying a shear. Okay, the shear doesn't matter for the z component of strain, but if you apply a stretch in the x direction and a stretch in the y direction, the plate or the element will essentially get squeezed or compressed in the z direction. So essentially, if it becomes elongated in the x and y direction, it becomes thinner in the z direction, right? That is the reason why you have a negative sign here. That is why the strain in the z direction is minus 2.357 into the minus 4. Okay, because it is getting smaller in the z direction. Okay, so that also makes sense. So now we have found all the unknowns. The last step is to actually arrange them into the stress matrix. Okay, and if you look at the stress matrix, because this is plane stress in the xy plane, you essentially have only these four components that are non-zero. Okay, any stress component that has a z subscript is zero. Okay, so essentially one of the rows and one of the columns is zero because this is plane stress condition. Okay, for the strain matrix, the normal strains are all non-zero. Okay, so the diagonals are all non-zero, and you have one of the shear strains, epsilon xy here, is non-zero because you have plane stress in the xy plane. Okay, but epsilon xz is zero, epsilon yz is zero because they have those shear strains have a z subscript. Okay, so that is how the stress and strain matrices look like. So I want you to kind of pay attention to this. Look at how the stress matrix looks for the plane stress condition and how the strain matrix looks for the plane stress condition. In the next lecture, we'll look at a plane strain problem where essentially the sigma and epsilon matrices will get interchanged. Okay, so with that, I'll conclude and I'll see you in the next class. Thank you.